and welcome to our video on section 6.2, Properties of Radicals. So I want to start just by reminding everyone of what it means to be a simplified radical. First, we want to make sure that all exponents in the radicand are less than the index. So again, the radicand is what's underneath the radical symbol, and that exponent needs to be less than the index. We shouldn't have any fractions left in the radicand, no radicals in the denominator, and we shouldn't have any radicals inside radicals. So to get us warmed up, we're just going to go through some simplifying of square roots, and then we'll move into applying these properties to cube roots and other more complex scenarios. So as a reminder, we can break apart something like the square root of 75 into the square root of 25 times the square root of 3 so that we can find or simplify the square root of 25 as just 5. And so our final simplified radical form would be 5 square roots of 3. And again, we're just going to continue with these kinds of problems. So if you want to work on your own and mute me just to see if you've got the hang of it, feel free to do that. All right, so next we're going to look at the square root of 363. And so we can, again, maybe we don't know of a perfect square in 363. So we would start by dividing by 3 to see if we can find anything. And sure enough, we get 121. So I'm going to separate 363 into the square root of 121 times the square root of 3. 121 is a perfect square, and the square root of 121 is 11. So our simplified radical form would be 11 times the square root of 3. In number 3, we have a fraction, and so we want to remember the property that says we can separate a fraction into two radicals, the numerator, which is the square root of 3, and the denominator, the square root of 16. 3 is not a perfect square, so it's going to stay under the radical, but 16 is a perfect square, and so that's going to come out as 4, and our simplified radical form would be the square root of 3 over 4. Moving on to number 4, we again have a we again have a fraction. 1 is a perfect square. We're going to put that as a separate radical in the numerator, and then we have the square root of 12 in the denominator. So 12 is not a perfect square, and we're going to remember that how to do what's called rationalizing. So I'm going to write the square root of 1 here, and I'm going to separate 12 into the square root of 4, which is a perfect square, times the square root of 3. So 1 is a perfect square, so I can take that out of the radical. 4 is a perfect square, so I can take that out of a radical. But then I still have a radical in the denominator. So just as a reminder, when we rationalize or remove the radical from the denominator, what we do is we multiply the numerator and the denominator by the same radical that's going to allow us to create a perfect square. So again, remember, a pair makes a perfect square, so I have 1 square root of 3. So if I multiply by a second square root of 3, that will lead me to a perfect square of 9. So now I have the square root of 3 in the numerator, and in the denominator, I have 2 times the square root of 3 times the square root of 3, which is the square root of 9. So then what I can do now is go ahead and take out the perfect square. The square root of 9 is 3, and when it comes out, it gets multiplied by the 2 that is already outside of the radical. So my final answer would be the square root of 3 over 6. As a reminder, remember not to try to simplify one number that's in a radical with a number that's not in a radical. So we cannot simplify the square root of 3 over 6 any further. All right, so let's look at one that has multiplication in it. 2 is not a perfect square, and 6 is not a perfect square. But because they are both square roots, we can multiply what's underneath the radical, the radicand, and we can get the square root of 12. we can then separate that into the square root of 4 times the square root of 3, because again, we're looking for those perfect squares. The square root of 4 is 2, and so we're going to end up with 2 times the square root of 3. We have another multiplication problem in number 6, and again, 10 is not a perfect square and 15 is not a perfect square. So we can multiply the radicans together to get the square root of 150. We're then going to look for perfect squares. So 25 is a perfect square that is in the number 150 or is a factor of 150. And so when I take 150 and divide by 25, I get 6. So we can separate it into the square root of 25 times the square root of 6. And because 25 is a perfect square, our final answer will be 5 times the square root of 6. And again, we're going to leave all of our answers in simplest radical form. All right, one more interesting property that's very helpful is shown in our next number 7. Because these are both underneath a square root, both 27 and 3, we can just think of this as 27 divided by 3, which of course is the square root of 9. And that's going to give us 3. So rather than trying to simplify the square root of 27 and find a perfect square, we can go ahead and just simplify what's ever under the radical as long as the index is the same. All right, and then looking at number 8, our last one before we get to some variations, we want to recall that what's outside the radical symbol would be multiplied together, and then what's underneath the radical can get multiplied. Now again, 12 does have a perfect square, so what I'm about to show is not the only way to do this problem, but I'm going to multiply the 5 and the 3 to get 15, and then the numbers that are underneath the radical, 12 times 6 is 72. So again, you could have also simplified the perfect square that's in 12, which is a 4, first, or multiply the 12 and the 6 together like I'm doing. So 72 has a perfect square in it. So 72 is 36 times 2. So I can separate it into the square root of 36 times the square root of 2. And again, we know that the square root of 36 is 6, and we're going to multiply it by the 15 that's already outside the radical, and then keep the 2 underneath the radical. 15 times 6 is 90, so our final answer is 90 times the square root of 2. All right, so we're going to look at the properties, some of which we have just used, but we're going to look at them in a summary format. And these are the product and quotient properties. And we've been using, in particular, 1 and 2, and then we're going to introduce 3. So, for example, in number 1, where we can take something like the square root of 18 and separate it into the square root of 9 times the square root of 2, that helps us to simplify. In a similar way, if we have something like the square root of 1/9, we know that we can, again, separate those the numerator and the denominator and simplify to 1/3. In the property that has this would be the km root of b, is how we would say that, we can separate it into the k root and the m root of b. And again, notice that we can change the order here. So as long as k times m, right, as long as we use them both in any order, then we can separate that radical. So let's take a look at when we might use something like that. If I had the 6th root of 25, I could use this property to simplify and say, well, because I know that 25 is a perfect square, I could make this the cube root of the square root of 25. So again, I'm doing that because 3 times 2 is 6, and I started with the 6th root. And in this case, what I have is I have a perfect square here that can actually be simplified to just 5. So my final answer would be the cube root of 5, which is a simpler answer than the one I gave you, which is the 6th root of 25. All right, so let's see how a few of those work in practice. And again, just going through with more cube roots than we are square roots, because that's generally what's new for us. And we want to keep in mind our perfect cubes. We learned a lot of them when we factored the sum and difference of cubes. But again, you want to be kind of familiar with those so that you can recognize them. All right, so I'm going to use the property that says we can multiply what's underneath the radicands to get 250. And I'm looking for a perfect cube, which hopefully we're thinking 125. And so I'm going to separate the radical into the cube root of 125 times the cube root of 2. And that will give me 5 outside of the radical and the cube root of 2. And again, that's multiplication. In a similar way, I can use the division property, and I have the cube root of 81 over the cube root of 8. 8 is a perfect cube, which allows me to simplify the denominator to 2. And in the numerator, I want to separate or look for a perfect cube. So 81 divided by 3 is 27, and 27 is a perfect cube. So I'm going to separate 81 into the cube root of 27 times the cube root of 3, and then I'm able to take out, again, the cube root of 27 is 3, and so I have 3 times the cube root of 3 over 2, and that would be my answer in simplest radical form. All right, so now we have a square root, which, again, we have a perfect square of 36, and then we have w to the 3rd. So we're going to just separate that into the square root of 36, the square root of w squared, and the square root of w. So then we're going to be able to take the square root of 36 and make it 6. The square root of w squared will be w, and then we have the square root of w. So again, that's going to be our simplified form. All right, so let's move on to something a little bit more complex. You may be tempted to take the square root of individual terms. However, we cannot do that. So this absolutely would not be 2a plus 2b. So if you're tempted to do that, remember the importance of putting things in factored form when we simplify. The same thing would be true here in terms of we would want to factor out the 4 and get 4 times the quantity of a squared plus b squared. So then, because again, when we separate our radicals, we would be doing that in terms of what it's multiplied by. So we can separate this into the square root of 4 times the square root of a squared plus b squared. And again, a squared plus b squared is not a perfect square. It is the sum of perfect squares. It is not a binomial squared. So therefore, we cannot simplify that. So that's just going to be 2 times the square root of a squared plus b squared. All right, and now we have the 8th root of 36. So we're going to use that 3rd property that we had, and we're going to think, well, 36 is a perfect square. So I can simplify this radical by thinking about the index of 8 as being 4 times 2. So I'm going to make this the 4th root of a square root. I'm going to put the 2 here even though we don't see it, just to remind you that we can do this because the 4 times the 2 is 8. And then I can go ahead and simplify the square root of 36. We know that that's 6. So my final answer would be the fourth root of 6. And again, that would be considered simpler than what I was originally given. All right, so here we have something in exponential form, and we want to recall that we can take that exponent of 8 and divide by the index of 4, but I'm just going to show this as separated into the fourth root of 4 times the fourth root of 3 to the 8th. Now, because 4 is a perfect square, we're also able to do something with this first radical. I can make this the square root of the square root of 4, and then I'm going to, again, think about the fact that with the exponent of 8, I can make this 3 to the second, because 8 divided by 4, this 8 divided by this 4 will give me the power of 2. And so my 9 that applies, when I apply that exponent, that's actually going to come in front of my radical. And I'm going to simplify the square root of 4 as 2. And so I'm going to be left with, again, because I have another radical, that's going to be 9 times the square root of 2. All right, so number 9 here for our examples, we have 12 to the 8th power is our radicand, and we have the 6th root of 12 to the 8th. So I want to be thinking about the fact that I can, that 12 to the 6th would be a 12 to the 6th would be a perfect root. So I want to see if I can separate that to simplify. So here I'm going to make this a cube root of a square root of 12 to the 8th. The reason I'm doing that is because then I've got that even index, again, the square root even when we don't see it, and that's going to allow me to simplify. So I'm going to highlight this part right here, right? The square root of 12 to the 8th, just that portion, would be 12 to the 4th, and then I still have the cube root that I didn't have highlighted. So now I've got the cube root of 12 to the 4th, and I can separate that into the cube root of 12 to the 3rd times the cube root of 12 to the 1st. So we know that here, because the exponent matches the index, I have a perfect root. So that's going to come out as 12, and I'm going to be left with the cube root of 12 for this portion. So again, that's fully simplified. All right, just a few more examples. We're getting just a little bit more challenging here. What we're going to do next is something that is, again, we reminded you in the beginning examples about rationalizing the denominator. However, when we have an index other than 2, we have to think about what we should multiply by in order to get the perfect, in this case, perfect cube in the denominator. So I'm going to separate the, as we know that we can do, I'm going to separate the fraction into, did I skip? Oh, I did skip one. Let me, this one's just a little bit easier to do, so I want to start with this one. So I'm going to separate this into the cube root of 5 over the cube root of 4. Now 4 is a perfect square, but it is not a perfect cube. So you want to think about the fact that to get to a perfect cube, I would need to multiply by 2 because 8 is a perfect cube. So, and I'm going to multiply both the numerator and the denominator by the cube root of 2. In the numerator, that's going to give me the cube root of 10, because I'm going to multiply what's underneath the radical, the 5 and the 2. And in the denominator, when I multiply the 4 and the 2, I'm going to get to the cube root of 8, which is a perfect cube. So now I have the cube root of 10 over 2, and I was able to rationalize the denominator. All right, so let's look at the next one. That's just, again, another example with rationalizing the cube root so that we can just make sure that we're understanding how it works. All right, so we have the cube root of 16 over the cube root of 27. Oops, I was wrong. This one does not require us to rationalize. So 27 is a perfect cube, so we are able to just simplify that. So the denominator becomes 3, and what I'm going to do with the numerator, 16 is not a perfect cube, but it has a perfect cube in it. 16 is 8 times 2, so I can separate that into the cube root of 8 times the cube root of 2. And of course, we can then take out or simplify. Cube root of 8 is 2 times the cube root of 2, and we still have our 3 in the denominator. So now we're in simplest radical form, and because again, we've taken out all of the perfect roots that are possible, and we do not have a radical left in the denominator. All right, so this one really is rationalizing the denominator. I will separate this again into the cube root of 2 over the cube root of 9. 9 is not a perfect cube, so I want to think about what could I multiply 9 by to get to a perfect cube. Well, 27 is a perfect cube, and if I multiply 9 times 3, I'm going to get 27. So I want to multiply the denominator by the cube root of 3, which means that I would also multiply the numerator by the cube root of 3. That's going to get me, again, I'm going to multiply the radicands. So I'm going to get the cube root of 6 in the numerator, and in the denominator, I'm going to have the cube root of 27. We created that perfect cube, so therefore we're able to go ahead and take that out and make that a 3. We are now in simplest radical form. All right, last two examples, just again, these include negative exponents to remind us of how they would work. So if I am evaluating or plugging in values, for example, x is 4 and y is 8 in this question, number 56 from the textbook, I'm going to go ahead and plug those values in. And then I'm going to get 12 to the negative 1. Now we want to remember that, again, we would write that on the other side of the fraction bar, which, again, there's no fraction bar here, but remember we can write that over 1. So we're going to write this as 1 over the square root of 12. Well, 12 has a perfect square in it, so we're going to take that out, the square root of 4 times the square root of 3, and that would give us 1 over 2 times the square root of 3. Well, we're left with a radical in the denominator, and so we know that we need to rationalize. This is a square root, not a cube root, so we don't have to think as hard. We're going to multiply the numerator and the denominator by the square root of 3 to create that perfect square, and that will give us the square root of 3 in the numerator, and in the denominator we'll have 2 times the square root of 9, which is, of course, 2 times 3, which is 6. And final, again, I know I mentioned this before, but don't be tempted to simplify something that's under a radical with a number that's not under the radical. All right, similar in that this is has a negative exponent, and so we want to think about how we would move that to the other side of the fraction bar. And in this case, because they are both square roots, we can just go ahead and move that right up to make that 27 x to the second, because when it moves up, we have x to the first times x to the first. And as a reminder, if we wanted to, we could just simplify that 27 over 3 to make that the square root of 9 times the square root of x squared. So what I did here was I simplified 27 over 3 and made that 9, and then I separated it into two radicals, the number portion and the variable portion. And so here we're going to get 3x. We don't need the absolute value around on the x because it originated under the radical with an odd exponent. So we only need to do that when we start out with an even exponent. That's when we are not sure of the sign and therefore need to use the absolute value. All right, so this concludes our video on section 6.2. Do the homework and bring your questions to class.